Okay, good morning, everybody. This is class 18. Do you know how many classes we have this semester? 28. We only have 28, so we're well past the halfway mark. I usually watch that and count down with a lot more enthusiasm than I have this semester. I'm actually kind of enjoying this semester more than I have the last few years, and I think that's largely to your enthusiasm, and you're a good group, not like those other guys from before, so you can tell them I said that. All right, so just to go over a couple of announcements here, what you've got coming up on your short-term schedule in fluids, you've got homework 7 due on Tuesday, and then that same day we're going to have our second of 2 quizzes for the semester. Remember that those quizzes are relatively low stakes as far as the points that are available, but it's a good midpoint check to see if the material is absorbing and taking root in the way that it should prior to the higher stakes exam that we'll have later on. So the coverage of the quiz will just be the material covered since the first exam, and so that means Chapter 4. The concepts in Chapter 4. So Euler's equation, Bernoulli's equation, the centripetal acceleration that we're going to be learning about today, different types of flow visualization, just those topics in Chapter 4. Yes?
So is that safe to assume it's like 1 to 2 questions most likely?
We won't have a lot of time, so my goal is for the quiz to take between 15 and 20 minutes. And I think what I'm going to do on this one is try and throw in at least one concept question and then one problem-solving question.
Makes sense because it's pretty easy to do math. It's a lot harder to remember concept very well.
That's right. Yeah, you got to be able to explain the material if you have any hopes of retaining it. Plugging numbers into equations, that doesn't stick in the mind as long as actually understanding a concept. So I need you to be able to do both. All right, so acceleration. We've been talking about how acceleration affects fluids. We've been talking about how non-uniform flow, which is caused by convective acceleration, causes a change in pressure due to that change in velocity. And the video that we watched last time, remember how we said several times that an increase in velocity causes a diminution in the pressure, and then the atmosphere on the other side causes it to, like in the case of the ping pong ball, stay in the funnel. So that was one type of acceleration. The local acceleration, you used Euler's equation to describe how pressure and elevation are affected by the change in velocity over time. Today's acceleration is the change in velocity when there's a rotational flow. And it's not that the magnitude of velocity is changing, but it's the direction of velocity is changing. And here's kind of an interesting discussion on centripetal forces. Sometimes people talk about centrifugal forces, and there are pumps that are called centrifugal pumps. This kind of goes into a little bit of the way that those words should be technically used. Sometimes they're used interchangeably. This gets a little bit into the weeds on the vocabulary, and that's not really the important point, but this kind of helps to visualize some of those forces, and so I thought it would be a good place for us to start. Okay, so the key things that I wanted to emphasize on this video is that if the mass of the object that's in rotation changes, so then does the force required to keep it rotating at the same radius. The rotational rate is going to play a role in the force that has to be applied, and so is the radius of rotation itself. And all three of those factors are accounted for in the equation that we're going to use to describe what happens specifically to liquids when they're rotated in that way. So here are the videos that we're going, here are the equations that we're going to use for some of the problem solving that we're going to do. The tangential velocity of a particle that is in circular motion and is being accelerated, therefore, in a radial fashion is the radius times the rate of rotation. And this omega has units of radians per second. And remember that in a circle, there are 2 pi radians. And when we're doing problem solving, the way that we'll substitute the units into the equations is just inverse seconds. Radians isn't really a unit when we're substituting them into equations. Like the 3 base units that all other units are derived from is length, mass, and time. All other units are just some combination of those 3, length, mass, and time. And so radians isn't really a unit. So just as a preview for what we do with the problem solving, if we have the rotational rate described in revolutions per minute, RPM, we're going to have to convert it into radians per second if we want to know the tangential velocity, or if we're trying to calculate the centripetal acceleration. So the centripetal acceleration is saying, how is this velocity's direction, the change of direction, not necessarily the change of magnitude of velocity, but how is the change in direction causing an acceleration? And so it's omega squared times the radius that it's acting about. Now, if we have revolutions per minute, it's given typically for pumps, it's pretty common, RPM, then we want to convert into radians per second. 1 revolution is 2 pi radians. And so if you have RPM, and the R in RPM means revolutions, then you'd need to multiply by 2 pi to get into radians. So just multiplying by 2 pi would then give you radians per minute. And if you want radians per second, then you have to divide by 60 because there's 60 seconds in a minute. So combined together, the conversion between RPM and radians per second is multiply by 2 pi, then divide by 60. All right, another brief video. All right, when we were talking about Euler's equation, the rule of thumb that I introduced is that the pressure and elevation increases in the opposite direction of acceleration. Do you remember hearing that before? Remember that if we have a tank of water and we accelerate it to the right, the pressure increases to the left. If it's an enclosed tank, then the water level wouldn't be affected. If it's an open tank and we have like a bucket of water, if you accelerate the bucket to the right, the water level gets deeper on the left. So that general principle still holds true here, that the pressure and or elevation increases in the opposite direction of acceleration. So here the acceleration is working inward towards the center about which everything is rotating. And so the acceleration is inward, but what's increasing in the opposite direction is the liquid level. And so we can see it from the sides here. The water level is greater at the edges than it is here. So why do you suppose that the liquid level is greater at the edge than it is right at the side? I mean, it's pretty obvious here that the liquid level is going to be deeper on this side than it is in the center, because why? It's in the opposite direction and it's further away. So we just have to think in terms of distance. Like, ooh, did I push the wrong thing? No, I didn't. Here at the corner, this is where it's furthest away from the center of rotation. The center of rotation, if we look down from above, this aquarium, here's the center of rotation, and so the point that's furthest away will be these 4 corners, and so we should expect the liquid level will be the highest at each of the 4 edges. And so what we need now is an equation that tells us what's the relationship between acceleration, pressure, and elevation. Because that's what Bernoulli's did, that's what Euler's did, is it gave us some formula to say what's the reaction of the fluid to the acceleration that occurs. And that's what we've got with the rotational flow equation. By the way, there's lots of different places where rotational flow is observed. It's observed in a tornado when the fluid, being air in this case, is acting in a circle. You can induce a vortex, a liquid vortex, with pretty simple equipment, like a little science fair experiment would be to take a couple of 2-liter bottles and shake them together so that the water is draining down through the bottom. And once you have the water draining down through the bottom, then the velocity of liquid traveling downward is enough to get it to continue to spin. So that's kind of a interesting I don't know, DIY visualization of a water vortex. In the types of problems that you're going to see in the homework assignment and during the lecture, we're going to look at these U-shaped tubes because it's a confining environment that keeps the liquid in a spot that we'll be able to observe it. And these U-shaped tubes also allow us to control the distance of rotation about the central axis. You can see here what's going on this U-shaped tube is it's open in both sides, so the liquid level is able to adjust freely depending on how quickly it's being rotated. This circular arrow just implies that it's being rotated about the left leg, and so as it spins, this right leg will alternate. It'll be on the left side of it, it'll be on the right side of it, but the liquid level rises the further away you get from the axis of rotation. So when this was in equilibrium, like before we started to rotate this U-shaped tube, the liquid levels were equal. There was no acceleration when it was just motionless and in equilibrium. But once an acceleration occurred, then the liquid level rises the further away you are from the center axis of rotation. And so here in this example, what they're saying is we have 2 points, one at the water surface inside, right at the axis of rotation, and then some other location where we usually are in the habit of picking, you know, location 1 and location 2 at spots where we know things. Now here's the formula, not Bernoulli's equation, but kind of similar to it in that the first 2 terms, the pressure head term and the elevation head term, are common to Bernoulli's equation, but this third term accounts for the centripetal acceleration. And so omega squared times radius squared divided by 2g, when we combine all of that together, and omega just has units of inverse seconds, this is going to have the same units of length as both of the other 2 terms, and so it can be combined. And as long as we pick 2 points where we know a few things, we can predict whatever else is missing. So just as an illustration, let's say for instance that we want to find out what is the rotational rate. We know for location 1, let's say that 1 is, let me just sketch this on the whiteboard, it's rotating about the left leg, and 1 is at the surface, and 2 is this other surface where it's further away. All right, so if we want to find out what's the rotational rate, we have some given information. We can say, for instance, that P1 is 0 because it's open to the atmosphere, and we're measuring pressure in terms of gauge. So the pressure at the interface of the liquid and the air is 0 at 1, and likewise the pressure at 2 is 0, since it's open to the air and air is touching at that interface. We can say that as far as measuring elevations, we can let the elevation datum be wherever we want. So we could measure elevation from the bottom of the U-tube, but the problem with that is we don't know how much liquid is below this interface. We could use the top of the tubes as our elevation datum, but that wouldn't work well either because we don't know how tall they are above the liquid surface. But what would be potentially a pretty good Z1 would just be to say, let's have the water surface itself be our elevation datum. And in doing that, we can say that Z1 is 0, and that allows us to say Z2 is 0.25 meters. Okay, so looking at the equation, what do we know so far? We know P1, that whole term's going to cancel out. Z1 cancels out. What about R1? The radius, what we're measuring is the distance from the axis of rotation. And so here's our axis of rotation about the left leg. The R1 will be 0 because it's right on the axis of rotation. So R1 is 0. R2, 0.10 meters. So we know everything in the equation, and assuming that this is water, it doesn't say what the fluid is, but I'll say it's water. I'd like you to try and solve for omega. What is the rotation rate in terms of radians per second? All right, so the information that we can get from the picture there is the pressure, radius, and elevation at 1 are all going to be 0. We know the radius and elevation at location 2, and the only thing that's not known is omega. So if we rearrange the equation to solve for the unknown rate of rotation, we should get that it's 22.5 radians per second. Okay, and then if we get some practice converting between radians per second and RPM, in this case, since we're going from radians per second into RPM, then we multiply by 60 seconds per minute. So now we have a certain number of radians per minute. And if we want to convert from radians to revolutions, we have to divide by 2 pi because there are 2 pi radians in a revolution. So that's 211.5 revolutions per minute, RPM. Any questions about our first exposure to the equation? We can do examples where the pressure is unknown. We can do examples where the elevation is unknown. And like this, where the rate of rotation is not known. This example also asks, what's the radial acceleration experienced in the right leg? So if we go back to the formula here, radial acceleration is going to be omega squared times r. So in the right leg, if omega is 22.15, we'll need to square that and multiply it by r. The distance from the axis of rotation over to the right leg is 0.1 meters. Okay, so the acceleration in the right leg is 49.05 meters per second squared. You can see how the units arise out of that. Remember, radians, they don't exist. Consider them as imaginary when we are looking at the units that come out of the equation. And then the final thing it asked was, what's the tangential velocity in the right leg? So given the rate of rotation and the radius of rotation, what is the velocity if we are looking down from above at this system as it rotates? What's the velocity of that tip as it goes around in a circle? And the equation for that, the velocity is the radius times the rate of rotation, so r times omega, and we should get that it's 2.215 meters per second. All right. So that was open to the atmosphere. You know, the type of question that is kind of interesting is when Like, what if this was sealed on both sides and then we started spinning? Think about what would happen if we sealed it and then it started spinning. So the fluid, the liquid, would be forced over towards the right. But if it was sealed before we started spinning, what would happen now is that we'd have pressurized air in the headspace above the liquid, and we'd have a vacuum in the left leg, and so that would moderate how much the liquid levels change. So if I wanted to be really crafty, I could come up with an idea where I'm telling you what's the pressure of the air in there, and I don't know, there's all sorts of interesting questions that can be asked, like vapor pressure type problems. Let's look at another example just to get some additional practice, and a different type. This one is, it's confined, it's sealed, and so the liquid level isn't able to respond to the acceleration that's occurring. Remember, what's responding to the acceleration is the sum of the pressure head and the elevation. In other words, it's the piezometric pressure that changes, not just the pressure itself. So sometimes it's going to be the liquid level responding, other times it's just the pressure. And here, it's sealed and full of liquid even before it starts spinning. But then once it spins, the liquid stays where it is, always. And we want to find out what is going to be the pressure here at location M. And we know the radius to location M from the axis of rotation. We know the radius out to some other secondary point where we've measured the pressure. And then in this case, the fluid is filled with a liquid other than water. This is oil. And so the fluid properties come into play because we're dividing by gamma when we find the pressure head. So I'd like you to try and calculate here, what is the pressure at location M? Now think about, compared to L, should it be higher or lower? Before we start crunching the numbers, just think logically, can we predict whether it's going to be higher or lower than the pressure where we've measured it? Here at L, we measure as 2.75 kilopascals. So first of all, consider the hydrostatic effect. Would just the elevation of point M give us any clue if it wasn't spinning? How would the pressure at L versus M be if it wasn't spinning?
Pressure at L would be greater than the pressure at M.
Excellent. That's right. So if it wasn't spinning, L would be greater, M would be less. Now think about it is spinning. Okay? So are we able to predict how the effect of it spinning, irrespective of its elevation? Just consider the fact of it's spinning and there's different radiuses there. Both sides have the same omega. You'll notice, by the way, in this equation, it's not omega 1 on the left and omega 2 on the right. It's just there's only one omega because it's all rotating at the same number of radians per second, regardless of what's the distance away from the axis of rotation. The entire system is spinning at the same omega. So that comment aside, so what do the radiuses predict about the change in pressure? Which one's going to have higher pressure because of the radius?
Pressure at L would be higher.
Okay, you're right. Why? How did you come to that conclusion?
Since it's farther away from the radius, water's forced out more.
That's right. Yep. There's more, there's a greater magnitude of acceleration as the radius increases. And so location L is experiencing more acceleration than location M. So both of those two trends, the fact that L is lower and it's further away from the axis of rotation, that means L is going to have a higher pressure than M. So when you plug and chug and you get some number, double back and make sure that it makes sense logically. Compare it to the expectations that we know should occur based on those two factors. Okay, so we have to convert from revolutions per minute into radians per second. So multiply by 2 pi, divide by 60, and that gives us 2.618 radians per second. By the way, if you just round that off to 2.6, then your answer is only going to be accurate to 2 digits. And so you'd only be able to say 1,300 pascals instead of, like in my case, since I have 4 digits of precision here for the conversion, then in theory I can predict the pressure to the nearest pascal. And that's assuming that the 25 radians per second that was, 25 RPM, that's assuming that that was exactly 25.00 RPM. The other thing we have to do is the preliminaries is use the specific gravity to calculate the unit weight of this particular liquid that's in the U-shaped tube. Rearrange to solve in terms of the pressure at the unknown location. And when we substitute in the numbers, some of the common mistakes that I see is people forgetting to square one of the terms. That's a pretty common mistake, like on quizzes and exams. In the end, we should get that the pressure at location M is 1339 newtons per meter squared. So 1.3 kPa. And what did we say? We thought it would be lower pressure because it was at a higher elevation and a reduced radius compared to L. So that worked out to be true. What if it was rotating in the middle? You know, it's lopsided right now. What if it was rotating exactly in the middle? What do you suspect would be the pressure differential between M and L? Well, in that case, the centripetal acceleration would cancel out on both sides, and it would just be equal to the hydrostatic effect. So the delta P would just be related to the delta H. We could still use this formula. I mean, it's not like this formula would give us the wrong answer if we went to the trouble. It's just that the R1 and the R2 terms would cancel each other out. If the radius are equal, then the pressure is described just by P1 divided by gamma plus Z1, and that's a manifestation of the hydrostatic equation. So this is saying it's the hydrostatic effect plus the effect of the acceleration. All right, so we've done 2 examples so far. One where we are finding what is the unknown rate of rotation. This one with a confined tube and the liquid level isn't changing. How does the pressure adjust due to a known rate of rotation? Let's consider another option. What if we have a system that's open to the atmosphere, and we can take these depth measurements before we start spinning it, but then we begin to spin it. And so after we begin spinning at 8 radians per second, it's going to come into a different water level equilibrium. This time we're not spinning in the middle. If we were spinning in the middle, then the water levels wouldn't change. But here it's lopsided again. So on one side the water level is going to go up, and on the other side the water level is going to decrease. So which is which? On which side will the water level increase? On the right, because it's further away. So in the same way that we knew the leg that's further away is going to have more pressure, well, here the leg that's further away from the axis of rotation is going to have more elevation, because that's what this acceleration is doing, is it's pushing the water out one direction. So let's just, before I turn you loose on this problem, let's consider what do we know and what do we not know. When we're trying to pick a spot that we know lots of things, it's pretty helpful for us to do pick a location that's at the interface of the liquid and the atmosphere. Why is it that we've used that location so consistently? Yeah.
There's a constant value most of the time.
Value for what?
The pressure of the atmosphere.
That's right. So we know that the pressure at the interface of the air and the water is 0. So that's kind of why I always say, well, let's make location 1 be here and location 2 be there. It's because we're trying to pick locations where we know a lot of information so we don't have too many unknowns in this formula. I mean, this formula works for anywhere in the system, but I can only predict something if I have all of the other bases covered in terms of the variables have a number to plug in. All right, so this is saying, what about when it starts spinning? What is going to be the equilibrium water elevations? So when it's spinning, it's going to have a little bit less water in the left and a little more water on the right. Does everybody agree so far? That seems logical. And so probably a good spot for us to pick for our location 1 would be at one of the interfaces, and location 2 would be at the other. So let's consider the variables. What do we know at 1 and 2? All right, there's P1 and P2. Well, at both of those locations, it's 0. Okay. What about the R terms? R1 and R2.
Well, the radius would not change.
That's true. So our radius is fixed. So we know R1 is 0.18 meters. R2 is 0.36 meters. Okay, so far so good. So what are we solving for in this problem?
Elevation.
Elevation. So it says find the equilibrium water elevations. We've got this one equation. How many unknowns do we have?
2.
Yeah, we don't know Z1 and we don't know Z2. So at first glance, it seems like we're temporarily stuck because we've got this equation, and Z1, well, we don't know. Z2, we don't know. All right. So is this class dismissed, or is there something else we can do? Is there another equation have you heard like 2 equations, 2 unknowns? You can solve it if you've got 2 equations that relate the same variables. So this equation relates Z1 and Z2 in a certain way. Is there another equation that relates what we know about Z1 and Z2? You're nodding your head, of course. There's got to be. It's so obvious from the way he's setting it up. But what might it be? Yeah.
Well, I don't know what that could be. Couldn't you just rearrange this one where you just take the height difference, it'd be Z2 minus Z1, and you put your 2 omega equations on the other side of the equation, so you'd have the height difference?
You're heading in the right direction. So what do you know about, let's put it this way. If it goes down 1 centimeter on the left, what happens on the right side?
It goes up by 1 centimeter.
It goes up by 1 centimeter. So that's a relationship. Knowing that relationship is going to be enough for us to solve the rest of the equation. So we do want to know the delta Z, that's true, but the actual water elevations, what we can say is, let's say the bottom of the tube is our datum. If our Z datum is the bottom of the tube, then we could say Z1 plus Z2 is what?
Would they be equal to 18 centimeters?
18 centimeters plus 18 centimeters, because there's the elevation of 0.1 above the datum initially, before it starts spinning. And then on the right side, it's at 18 centimeters. And so 0.18 meters plus 0.18 meters. So together, Z1 plus Z2 is 0.36 meters of water. So this column height combined, there's 0.36 meters of water in the vertical part of the U-tube. I mean, there's also some water down here in the base but the vertical amount of water is 0.36 meters. So if it goes down 1 centimeter on the left, it goes up 1 centimeter on the right. So it could be like 17 and 19 centimeters, and the sum would still be 0.36. Okay, so what I'm saying is, we can use this equation and that equation to find out what is in absolute terms, not just in relative terms, not just what's the difference in z. We can find out what's the actual equilibrium height elevations of 1 and 2 when it's spinning at 8 radians per second. So another way we could say this z1 plus z2 is 0.36. We could also say z2 is 0.36 minus z1. That's another way. That's the same equation, right? It's just maybe that's going to be more useful.
So we can, in theory, substitute out C2 for the moment and put that equation in to find our value.
Yeah, there's only one unknown if we do that. The only unknown will be z1. All right, so let's try that. It's already in the radians per second, so we don't have to monkey around with converting it. Try and solve for z1 and z2. Okay, so on the right side, which is the one that's further away, it'll rise up to 0.3385 meters, and then on the left side, it will go down to 0.0215 meters. So lots of algebra along the way, just rearranging the equation to solve in terms of the unknown elevation. And it's easy to make a mistake forgetting one of these squareds in the rotational rate or one of the radii. So don't accidentally miss one of those. But any questions about this? So remember, spinning brought it down on the left and raised the liquid on the right. And this is the equilibrium water elevations if it's spinning at 8 radians per second. What if we spin it a little bit more? So think about, it's most of the way down so far. It's pretty far down. We have an equation that we can put in terms of, let's see, this equation. It gives us Z2 for some rotation rate. So right now it's for 8 radians per second. Substitute in what if we start spinning it at 14 radians per second? What is the Z2 if you increase omega from 8 to 14? So we're considering the second part of this example. What if the rotational speed increases to 14 radians per second?
So we'll eventually reach a point where all the water on the left side will be 0 on the elevation? Okay. The water out of the middle of the tube?
Mm-hmm.
That's what I thought.
Okay, so what we're doing here is substituting, instead of 8 radians per second, what if it's spinning at 14 radians per second? So that same formula, if you put in 14 radians per second and we still have the same radius, you know, it's 18 centimeters over to the left leg, 36 centimeters over to the right leg. Well, that means that the water level should be up to 0.66 meters on the right And if you substitute it into our original formula where the sum of the z's is 0.36, that implies that the liquid level would be below 0 on the left. But it can't do that because of the confining nature of that tube. Like the tube isn't going to allow the water surface to go down below where the tube actually is. So what happens when we keep spinning it more and more and more is the liquid level continues to rise on the right side, but where is that water coming from? The interface goes down, and then the interface actually enters the base leg. And so we need a new equation that relates how tall is the water on the right to where is the liquid inside of the base leg. So we need not an equation that's like Z1 plus Z2 is 0.36. That's valid as long as the liquid level isn't inside the base. But then once the liquid is inside the base, things are a little bit different. Since we're short on time, I won't ask you to try and figure that out, although it's not a great mystery. It's just what we will say is that the elevation over on the right side is going to be the 0.36. So when all of this water is over on the right, that means it's 0.36. So that's going to be how much there is. And then how much of the base has shifted over to the right. So the relationship becomes in terms of R1 plus the total vertical liquid that's now all in the right base leg. So this becomes our other equation of how we relate what is the unknown Z2. Z1 becomes a known, in other words. When the water is down on this side, so let's say the water's here someplace. Well, now Z1 is 0, but we're not sure what R1 is. We're not exactly sure how far away it is from the axis of rotation. So the unknowns are R1 and Z2. But together, we know that the sum of the liquid that's available is the 0.36, and then however much the liquid level has retreated in the base leg. So this is our new equation, and just to show you how we could solve for it, when it's spinning at 14, how high does the liquid get over on the right side? So we're substituting into the equation the rotational rate of 14. R1 is unknown. Z1 is 0. The pressure at both of those locations is still 0. The unknown is going to be the depth on the right side, and then R2 is known, omega, the rotational rate's known. So the only unknowns are the radius and then the Z at location 2. So you can see here that I've substituted in, instead of Z2, I've substituted in this relationship that relates the total vertical elevation of the water and the radius at 1. So that's what happens, is the liquid is in the base rather than just on either side. Any questions about this example? Yeah.
So you ultimately got your the radius answer to be because of a quadratic formula?
No, I don't think so. I don't think it is related to the quadratic equation. I think that...
well, I was looking on your final step there to get the R1 value.
Oh, right, yeah. So we find the roots of the equation. So do you have like a solver in your calculator? I know most of you use the Casio calculators, and you can find the roots of an equation with that. So yeah, you'd get a negative root and a positive root, and so what the negative radius means is that it's actually to the right rather than being to the left of that axis of rotation. It couldn't be that the radius is 0.32, because 0.32 would be further than that base leg actually makes available. Like, it's only 18 centimeters. So the liquid level, the radius couldn't be 32 centimeters. So negative means that the liquid level actually is retreated over to the right side of the base leg. Yeah. Okay, so just to refresh your memory about these announcements that apply, the quiz and the homework assignment, both of those come to fruition on Tuesday. If you have any questions on the homework, feel free to stop by during my office hours or send me an email. I'll do my best to respond. So I will see you on Tuesday for the quiz.